Go. Start video. Hey, we've got Taylor with us. Good going. All right. Let's see who we got here. We've got we got a good crowd. We've got Alex. We've got Nathan, Braxton, Tyler, Brian, Daniel, Bryce, William, Taylor. We have a wonderful class. There's Nicholas, Taylor, Nathan, William. How about it? Do you have any questions for me?
Morning, Professor. I do have a question. This is Nathan.
Yes. Yes, Nathan.
I can't remember. I know last week Mohammed had a question about that nitrogen problem and there not being a English table for it. I forget what you said.
You can't do a PV diagram. However, it's an ideal gas. Air is treated as an ideal gas, and it's what, 70-something% nitrogen. But I'm not going to count off on you guys on a PV diagram, so don't worry about it.
Okay.
Did that answer your question okay?
Yeah, that's fine. Thank you.
Yeah, we don't have a nitrogen. But since it behaves like an ideal gas, we can use any ideal gas equation. Anybody else have a comment or question? Okay, well, let's see. We've studied nozzles and throttles, I believe. And we need to do turbines, I know. Yeah, I think we need to do turbines and compressors. Okay. All right, that's what we're going to do. We're going to do turbines and compressors. If we have time, we'll do a condenser. But let me write the first law up here, which we know and love, or we're starting to know and love, I hope. Now we can put summation signs on some of these here. In case you have more than one input, for example. Ta-da! I just wrote the first law of thermodynamics. And we're going to do a turbine. Now, the one I thought we could do is problem 430. Let me find it here. 430. Okay. Actually, you know what this is? This is a very small, high-speed turbine. It's a dentist's drill. When you go to the dentist these days, the drill they have works on compressed air. And it goes. Sound familiar? Yeah. And hey, you know, when I was a kid, they didn't have those. They weren't invented yet. The drills they used on my teeth had pulleys and yeah, they had pulleys and they turned, and there was about 2 or 3 pulleys on this crazy thing that came over there, and he stuck it in my mouth and turned the thing on, and it didn't make that. It didn't make that sound. It made kind of a grinding sound. You know what? I don't think everything's been invented yet. I think there's still stuff out there that could be invented. And whoever invented that dentist's little turbine drill like that, they're probably doing okay economically. But anyway, back to our problem. 430, it's a high-speed turbine, compressed air. You always start off by doing the device sketch. So here goes. Here's the turbine. The symbol kind of looks like that. And this is going to have air in it. And it's coming in. It has a power output of 100 watts. That's not very much, you know it. 100 watts, it's just like a 100-watt light bulb. The initial state is 400 kilopascals coming in, 50 degrees Celsius coming in. The exit state is 150 kilopascal minus 30 degrees. Assuming the velocity is to be low and the process to be adiabatic. You know what that means? That means we don't need to worry about the adiabatic. There's no heat transfer. And the velocities are low, so you don't need to worry about them. This drill isn't going up or down, so you don't need to worry about the elevation of it. And the MI and the ME are the same. You don't need to worry about the incoming and exiting because they're the same. And you know what? This is 0. This is 0 because none of these properties change with time. See, this is a derivative with respect to time. And you see that 400 kilopascals? The whole time the dentist is drilling your teeth, that's still 400 kilopascals. It's not changing any. At 50 Celsius, it stays the same. None of the properties change with time. Now they change with location. See, that's 400 kilopascals and that's 150 kilopascals. That's a change in pressure, but it's with location, not time. See, that 150 an hour ago or whatever, 10 minutes ago is the same as it is now. So that they call that steady state. In a steady state, that term is 0. So here's what your first law will look like. Put that power term over there on the left side of the equation. Throw out all the stuff you don't need, and that's it. You're looking at it. Isn't that nice? That's your first law in this particular problem. Now, there might be a turbine problem where you do have to include some other terms. It might be a multiple input or exit type situation. But for our little problem here, 430, that's it. You're looking at it. And hey, we know what this is. Do we know what the m dot is? Let me read it. No, we're supposed to find that. See, this is called the mass flow rate. We're supposed to find that. Okay. We'll work on that. Now let's see if we can get these. Now here's my plan. HI minus HE, that's the negative of HE minus HI. And you know what that is? That's just delta H, huh? And we got an equation for that. It's C sub P delta T. Now, C sub P for air is 1004 kilojoules per kilogram Kelvin. Now, don't forget there's a minus sign in front. We better don't forget the minus sign. And now we're going to do the change in temperature. Well, I'm getting a change in temperature of minus 80. Now, I know it's Celsius, but the amount in Kelvin is the same as in Celsius, the change. If you go from 50 to minus 30, you have a change in temperature of, it's negative. You got colder. Hey, there's two negatives that makes a positive, and so here's what you have. You have 1004 times 80. I'm getting 80.32 kilojoules per kilogram. Okay. Hey guys, we just figured out what this thing is. This thing right here is 80.32 kilojoules. Hope you can read my writing. That's supposed to say kilojoules per kilogram. And this is 100 watts. Now, don't get confused now. That W stands for watts. That W dot stands for power. And it's equal to 100 watts. So we have 100 watts is equal to m dot times 80.32 kilojoules per kilogram. Now here's where we could foul up. Because this, when you multiply kilograms per second times kilojoules per kilogram, you're going to get kilowatts. But see, that's not kilowatts, that's just watts. So what you have to do is, you can either have kilowatts on both sides or you can have watts on both sides. But you can't have kilowatts on one side, or I mean watts on one side and kilowatts on the other. Does that make sense? Here's one way of solving the problem. Multiply by a K and divide by 1,000. And so, or you could think of it as this way. Think of it this way. Multiply by kilowatts and divide by 1,000 watts. Because see, that's what a kilowatt is. It's 1,000 watts. But see, that way you get rid of the watts, and you'll have, well, what you'll wind up with is 0.1. Here, let me write that here someplace. What you wind up with is 0.1 kilowatts equals m dot 80.32 kilojoules per kilogram. Okay, go ahead and find the mass flow rate. Go for it. All right, I'm going to call on one of my excellent students here. Maybe, hey, William, unmute and say hello, please.
Hello?
Hello. Hey, William, have you plugged this in and got the mass flow rate yet?
Yes.
What'd you get?
0.001245.
You know what? That's what I got. Yeah, I got the same thing, William. I got the mass flow rate is 0.001245. Now, what's the units?
I'm not too sure.
Think about it. I'll give you time to think about it. We gotta know what the units are, or it's useless. Units are very important. You know that, don't you, William?
Yes.
Yeah. Have you come up with anything yet?
No, but should it be kilograms per second?
That's it. Kilograms per second, that's exactly it. Now let's look and see. I've got an answer book here. Let's see if that's what they got. This was problem 430. It was a turbine that uses air. And the answer book says, answer book says 0.00125 kilograms per second. Yay, that's what we got. Well, I think the answer book rounded off, but I'm pretty happy about it. Now there's one little fly in the ointment here. We always do something on these problems, and we didn't do it. What is that? We'll pick on William again. William, what is that thing that you always do when you do these problems that we didn't do, William? What is it?
A PV diagram?
Yes, very good, excellent. Okay, well, let's do that. It won't hurt us any. Let me see here. I need some room. Okay, we're going to do a PV diagram. Now it's air, so don't put a vapor dome thing on there. It's not going to liquefy. Now the truth is, air can liquefy, but you got to get it pretty darn cold. And under pressure, the pressure has to be a big pressure and it has to be cold, we're not going to liquefy. And so what we're going to do is we're going to draw our process. Why don't I shut up a minute, and you students on your scratch paper there or whatever, you draw the process, and in a minute I'll draw it and we'll compare. We'll see what we think. Go for it. I'll shut up. See if you can draw the process there. And label it. I want it labeled. I want some numbers on there. Well, okay, let's put that process on the PV diagram. Now let's put our isotherms on there. Now isotherms go like this. See, there's your 50-degree isotherm. There's your minus 30-degree isotherm. And we're going to go from 400 kilopascal. Puts us right there. There's state one coming in to 150 kilopascals. 150 kilopascal. That puts us right there. Yeah, there you go. There's state one, there's state two. And see, I've labeled my pressures. I've labeled my temperatures. I could even find these specific volumes if I wanted to. I could find those specific volumes if I wanted to. But I'm too lazy to do it right now. But here's how. You'd go P1 V1 equals RT1. That, you know, everything. You could find those. And by the way, this is a typical shape for an adiabat. See, these here are isotherms. Well, those are isotherms, but adiabats are steeper. No, notice it's steeper. Like if you had a little car here and you're going up a hill here, here's a little car, put, nee, 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 nee. You know what? A little car here going up this hill, put, ring, 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 ring. That's steeper, isn't it? Guess what? Adiabats are steeper. Is that how you spell steeper? I think it is. They're steeper than isotherms. Adiabats are steeper than isotherms. Okay, well, great. Any questions on that problem 430? Okay, well, let's do some compressors then. Why don't we do an air compressor first? If you're happy, I'm going to erase this and we're going to do a compressor. Okay, now there's something you need to know about compressors. They're opposite turbines. Everything's opposite. Instead of going from 1 to 2 here, the turbine or the compressor goes up the opposite direction. The pressure goes up. Well, that makes sense. If it's a compressor, the pressure goes up. Instead of the pressure going down, like in the turbine, the pressure is going to go up. Everything's opposite. In a turbine, the temperature goes down. Look, you got colder. What was it, 80 degrees colder? Turbine, the temperature goes down. Well, in a compressor, hey, we already knew that. In a compressor, they get hot. Compressors get hot. When you compress a gas, it gets hot. Yeah, everything's opposite. Now, on this here, turbines provide you with power. That's what the dentist used to run his drill there. It provides you with power. But compressors don't provide you with power. They require power. You have to find a source of power for the compressor. You could plug it in, or your compressor on your automobile runs off of your engine, your automobile engine. You have a compressor on your air conditioner in your automobile, and it gets its power from your engine. Compressors require power. Everything's just opposite. Well, here, let's do one. Here we go. I'm going to erase this unless there's a comment or question. Okay. All right, here we go. We're going to do a compressor. This is problem, let's do 439. We're going to do problem 439. Let me find it here. It says 439. An airflow is brought from blah, blah, blah to something here in an adiabatic compressor driven by a 50 kilowatt motor. What's the mass flow rate, exit volume flow rate? All right. When you know the drill, the first thing you do is the device sketch. We're going to do the device sketch. Only this is not a turbine, it's a compressor. And when you go to draw the compressor, it kind of looks like this, and you have to input power. We're going to do 439. Now, what did they say? The input is 50 kilowatts. So you got input power is 50 kilowatts coming in. There you go. And let's read it here. It says, the air it's air. You're dealing with an air compressor, and you're coming in at 20 Celsius, 100 kilopascal. Now, you know what? That's pretty much atmospheric temperature and pressure. but you're going through the compressor and you're coming out at 1,000 kilopascal and 330. Hey, it got hotter, didn't it? 330 degrees Celsius. Well, that's all the facts there. Now we could draw our PV diagram. There's your device sketch. I think I'll shut up and let you do the PV diagram, and then I'll do it, and we'll compare notes. Go ahead. We have a minute. See if you can put in some isotherms there and draw your process. Well, I don't know if that was long enough, but let's go ahead. I'm going to draw the isotherms now. We've got a 20-degree isotherm that goes kind of like that. And we have a 330 isotherm that kind of goes like that. And we're going from lower pressure, 100 kilopascals down here, to way up here at 1,000 kilopascals. Here's state 1, here's state 2, and it's an adiabat. It's just going the other way. See, this is 1,000 kilopascals. So we've done our PV diagram. And you notice that the adiabat, that's called an adiabat. What it is a process where there's no heat transfer in or out. No heat transfer. You know what's confusing to students is they hear that there's no heat transfer in or out, so they think it's going to stay the same temperature, but that's not true. In a compressor, they get hotter. The temperature changes, it gets a lot hotter. Look, we went from 20 to 330. That didn't stay the same temperature, did it? No. Adiabats are not isotherms. In fact, adiabats are steeper than isotherms, and they can very definitely change their temperatures. Okay, now what? Well, we've done our device sketch, we've done our PV diagram, and we labeled and put our process. See, that's the process. I want to see a process. I want a 1, I want a 2, I want a process going from 1 to 2 with an arrowhead on it to make me happy. Do that. Then what do? Well, you use the first law. Now, this is the first law for control volumes. See, control volumes have mass coming in. See, there's an m dot coming in and an m dot coming out. In fact, are we supposed to find it? Let me read this. 439. Yeah, we're supposed to find the mass flow rate. They also wanted the exiting volume. They wanted the exiting volume flow rate. Isn't that what it says there? Yeah, exit volume flow rate. They want to know what that is. Well, we'll get it. But the next step is our first law of thermodynamics. Now, this is 0 because it's steady state. This is a compressor, and nothing is changing with time. Whatever the energy is inside this compressor, it doesn't change over a half hour or an hour. It's the same amount of energy. Now, you are changing properties with location. Look, pressure's changing, temperature's changing, specific volume's changing, enthalpy is changing, but not with time. Now this is 0, that's 0, this is 0. And I tell you what we can do, we can put this W over on the other side, like that, W dot, that's power. And it's going to equal your m dot times HI minus HE. We're throwing out these other terms because they are negligible. That's the same thing we had before. But now they gave us this. They said this is 50 kilowatts. But now watch it. It's a negative 50 kilowatts. See, when the power is positive, that means your system is producing power. But compressors don't produce power. They use power. Remember, the turbine, the power was coming out. It was doing work on the environment. So that's a minus. M dot we don't know. And remember, we did that too. We went through that. Let's go through it again, make sure we understand. HI minus HE is equal to the negative of your delta H, which is equal to the negative of C sub P delta T, which is equal to the negative of 1004 kilojoules, kilogram, Kelvin. Now the change in temperature this time is 310, and it's positive, isn't it? Now I know it's Celsius, but Kelvin has the same change. Do I need to explain how come going from 20 to 330 in Celsius is a change of 310 in Kelvin? I'll be glad to if anybody wants me to. I guess you're okay. All right. Well, now let's do that. Here we go. Plugging this in now. And I'm getting 1004 times 310. I'm getting a minus 311.24 kilojoules per kilogram. See, the kelvins go bye-bye. See there, the kelvins cross out. Ah, looky here. We just figured this out. This is a minus, here, let's put it down here. This here is a minus 311.24 kilojoules per kilogram. Okay, and now we're going to solve for m dot. I'll shut up. Go ahead. Solve it for the mass flow rate. And I'll call on somebody here. Okay, I'm gonna call on somebody. Let me find somebody here. Tyler, unmute and say hi, please.
Hello.
Hello. Tyler, have you got the mass flow rate from this equation yet?
I believe so. I got 0.1606 kilograms a second.
That's what I got. Good going, Tyler. So we're pretty happy with that. We've got our mass flow rate. Now they wanted, I need some room here. I need room. We're gonna have to sacrifice some stuff here so I can have some room to work. They wanted this V dot, the volume flow rate. And what it is m dot times little v. Well, we know m dot, we just got it. Tyler just told me what that is. Now they want the exiting volume flow rate. So we're going to have to get the exiting specific volume. So here's how we're going to do it. We're going to go PE VE equals RTE. Now PE is 1,000 kilopascal. R is 0.287. And exit temperature, we're going to have to add 273 to that. So it's 3, maybe I did that right. Let's hope. Okay, find the exit specific volume there, and then find the volume flow rate. I will shut up here for just a tiny minute. I'll give you a minute. Go for it, and we'll get the volume flow rate. Well, I got an answer for the volume flow rate. Let me ask one of you guys here. Taylor, unmute and say hi, please.
Hi, please.
Okay, Taylor. Hey, did you get the volume flow rate from this equation by plugging in your little specific volume there?
I'm almost there.
Yeah, take your time. I'll look up what the answer book here says, Taylor, and we'll see if we got that together correctly.
Okay, I got a number.
Yeah, go far away. What'd you get?
0.0278.
That is what the answer book got. I mean, miracles can happen.
Yes, they can.
Yes, I feel good. But now, Taylor, we've got to know the units. This is called volume flow rate. we've got to know the units.
Cubic meters per second.
That's it. Jolly good show. It's cubic meters per second. And that's precisely, exactly what the answer book got. They got the same number, 0.0278 cubic meters per second. So we're doing good. Let's do another one. But before we do, is there any question on this 439 compressor problem? Okay, well, let's do one maybe a little harder. I'm going to erase all this. And we're going to do one with a refrigerant. Now this is 437. And 437 uses R134A. That's what you have in your car. If you have air conditioning, you've got R134A in your air conditioner in your car. Okay, let me find it. 437, there it is. A compressor brings R134A from 150 kilopascals, blah, 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 to 1200 kilopascals. It's water cooled, heat loss estimated. Now this one, sorry, I erased my first law now because this one has a heat loss. See, compressors get hot and they'll radiate heat out into the environment. And this one's radiating 40 kilowatts out into the environment. They give us the work and they want the mass flow rate. Okay, well, the first thing we got to do is draw a device sketch. And we have to label it. Now, you guys can sit there and watch me do it. And I'll have all the fun. Tell you what, I'll give you a minute. Draw the device sketch and put the input and output on it. I'll shut up. Go ahead. We're doing problem 437. Does everybody have, can they get to 437? Maybe I should write it down for those of you that are having trouble pulling that up. Here, let me write down some stuff. We're going to go from 150 kilopascal minus 10 Celsius, 1200 kilopascal, and then we're going to go. It's not an adiabat anymore, though, because there's a heat transfer, and we're going to go to wait a minute, I did that wrong. 150 kilopascal minus. Okay, now this is no, that was wrong. We're going to go to 1200. I wrote that wrong. 1200 kilopascal, 50 degrees Celsius, and it has a heat loss, which means that Q dot is a negative. It's negative, and the work is 150. Now, will that work be plus or minus for a compressor? Will the work be plus or minus for a compressor? Uh,
will be minus. Or
It's
sorry.
minus. It's minus. Compressors don't produce work. They require, I should say power, not work. Power is work per time, but they require power. Okay, go ahead and draw the device sketch. Well, I'm going to draw a device sketch. Now it's a compressor. So it's a gadget that kind of looks like this. And you're coming in here. At 150 kilopascal minus 10 degrees. And then you're coming out at 1200 kilopascal and 50 degrees Celsius. Now, the work is minus 40. Now, the way that works, or the power, I mean, the power is going in. See, that's negative. If power is coming out, it's positive. Now the heat transfer is just the opposite. The heat transfer is going out, and it's negative. See, if it was positive, it was going in. It would be going in. See, power and heat transfer, they're not consistent, are they? See, power going in is negative. Heat transfer going in is positive. It's not very consistent, but that's the way it is. That's the way they're defined. If you're losing heat to the environment, which we are, 40 kilowatts is being transferred to the environment, that's going out, and it's negative. Whereas work is being done on a system, that's considered negative. It's going in. Hope that's not too confusing. But there's the device sketch. And we can do the PV diagram. It's going to kind of look like that PV diagram we just did, where something is steeper than something else. Do you remember? Only I don't think it's an adiabat anymore. It's going to look like one, but it's not a real adiabat because the heat transfer is not zero. But it's still going to look like that other one. Here we go. We'll do the PV diagram now. Now we need a -10. I like those in red. We're going to do our isotherms in red. Here we go. -10. Here's your -10. And here's your 50. And you're still going to go from low pressure to high pressure, aren't you? You're still going to go from 150 kilopascals up to, here's 1, here's 2, up to 1200 kilopascals. Kind of looks like an adiabat, but it's not really. If it was an adiabat, I'll tell you what it would have done. It would have been hotter. So you're losing some of your energy with that heat transfer. The adiabat would have done this. See if this makes any sense. The adiabat would have come up here to the same pressure now, but it would have been hotter. Now, I don't know what this temperature would have been, but it would have been hotter. But the reason why it's not that hot is you had a heat transfer out. Did that make sense? Now, I could show you exactly what this new temperature would be. Call it, I don't know, T3 or something. It would be hotter than 50. And I could show you what it was, but we got other fish to fry right now. But there's your PV diagram. Now let's do our first law and solve this problem. Now, what did they want us to find? Let me read it. If you just woke up from a daydream, we're doing problem 437. They want the mass flow rate. Well, back to the first law. I shouldn't have erased it, but there's some room right here. Here we go. dE dt equals Q dot minus W dot plus M dot HI. We're going to throw out all those other terms. We don't need them for this particular problem. HE, a little bit lazy there. Coming in, going out, it's the same. Now let's put in some numbers. This one's going to be 0. This one's going to be minus 40. It's not 0 on this problem, is it? And then you have a negative. Now watch it. Here's where we could blow it. That negative is from your first law of thermodynamics. But we've got another negative here, negative 150 kilowatts. The power is negative, so you have a subtract a negative. You're going to wind up positive, aren't you? Plus your M dot. They're both the same. You don't need incoming and exiting in this case. And what you have is HI minus HE. Well, now we've done that twice before. We should be getting the hang of it. But you can't use that C sub P. What did we use before? We used this here, C sub P delta T. We can't use that this time. And I'm going to ask one of my best students why it is that we can't use that. We've done it twice before. Remember, that was 1004 times. Let me go to one of my wonderful students here. We're going to go to Nicholas. Nicholas, unmute and say hello.
Hello.
Nicholas, twice before, we use this equation, but we
Yes.
can't use it on this problem. Why is that, Nicholas?
I do not know, but if I have to make a guess, is it
Make a
because it's
guess.
not air?
That's a pretty good guess, Nicholas. It's not air. So if it's not air, what do you do then?
I do not know, Professor.
Let me tell you something. It's not only not air, it's not an ideal gas, is it?
No.
No. Now, if you don't have an ideal gas, can you use ideal gas formulas, Nicholas? Can you?
No.
No, you can't. Well, what do you use instead? You can't use ideal gas formulas because it's not an ideal gas. But you can use something else. What's the other thing you use, Nicholas?
A table?
Yes, that's it. He's got it. He's listened to me. You use the tables. Okay, well, let's do it. Let's go to the tables. Now we need the incoming specific enthalpy at 150 kilopascals and minus 10. Go to the back and start snooping around and find a 134A. I'm looking for it. I don't see it yet. Yeah, here we go. 134A. Now what I want is 150 kilopascals minus 10. By Jove, there it is. I need to write that someplace. You see that little HI right there? I found it. It's 393.84. 393.84. But I'm going to wait till I hear several uh-huhs before we go on. Can you find little hi 393.84 for 150 kilopascals minus 10 degrees Celsius in the tables? The table we want is B.5.2. B.5.2, and I'm waiting for some uh-huhs. Hey, there's one. There's another one. I need a couple more.
That's
And I think that might have been one. Anybody else? Can you find it?
Uh-huh.
Yeah, good going. Okay, good. Now let's find this HE here. See, in this equation, we need the exiting, that little e stands for exiting specific enthalpy. And what we want is 1200 kilopascals, R134A, same table, it's, what do they call it, B.5.2? And we need 1200, well, actually, yeah, B.5.2, 1200, 50 degrees Celsius. Hey, I found it. You know what this is? It's 426.84. See the exiting specific enthalpy. The exiting specific enthalpy is 426.84. And I'm gonna wait until I hear 2 or 3 uh-huhs on that. Can you find that? There's one. Give me another one. 426.84. You look up 1200 kilopascals. There's one. It's table B.5.2. Give me one more.
Uh-huh.
Yeah, great. We're doing great. Okay, now come here with me. I'm going to circle these. Look here. We just figured out HI. We got it sitting here. We just figured out H little e. We got it sitting here. We know everything in this equation except the m dot. Now I'm going to shut up. You've got a minute or so. Can you find the mass flow rate? Go for it. This was problem 437. Well, I got an answer. I got an answer of three point, a whole bunch of threes, kilograms per second. How about you guys?
Uh-huh.
Yeah,
Yep.
good going. Good going. We figured out the mass flow rate.
Professor, I got a question for you.
Sure.
This is Nathan. We can still use PV equals RT to label our PV diagram if we want to.
No, it's not an ideal gas. PV equals RT only works for ideal gases. You can't use it on this.
So we can use the
Ah,
tables if we want to label it. We'll just use the
Nathan,
tables.
Nathan has just, I did this all wrong, and I'm going to give Nathan a humongous thank you point, because you know what I did wrong, Nathan? I didn't put my vapor dome in there. This is all wrong. This is all wrong. Here, let me do it right. Let me do it right. We got time. We got eight minutes left. Now, if you'd done this, if you'd done that PV diagram like that, you would have gotten a 3 on your homework. And so that's what I get on mine. I get a 3 because I did that wrong. But I'm gonna do it right now. I tell you what, guys, what's important in life is you're gonna mess up. And what you want to do is you want to get back up and get back in the game, right? This thing's got a vapor dome. Now let me do this. Let me do this. That's for Nathan there, I believe it was, that helped us out on that. Let me find this again. I got lost. 134A. Okay. There it is. I'm going to go to the vapor dome table there for 134A and see this temperature up here is 101.2. That's the critical temperature. And this pressure here at the top of the dome is 4,064. I'm looking at table B.5.1 is what I'm looking at. Now I'm going to put in my stuff here. Let me make this a little bit further down here like that. I need the room. We need a 50 degrees Celsius. And that's going to be right about here, maybe. There's your 50 degrees Celsius. And then we need a minus 10 degrees Celsius. Make that even more down there where I can find room to put it. I'm trying to make up for the bad job I did on that PV diagram. Now here's the minus 10. There's your minus 10. Okay, now we're starting off at 150. Here's state 1. We are in superheated vapor. We're 150 kilopascals. And we're going to go to 1200 kilopascals. That'll be right in here someplace. Here's your 1200 kilopascals. And here's your state 2. And here's your process. It's not an adiabat, but it's kind of similar. The thing is, you've got a heat transfer out of whatever it was. I forgot. Was it 40? I got lost. Yeah, you had 40 kilowatts transferring out. But if you did your process correctly, which I didn't do, I was wrong. This is what it should look like. You should have a vapor dome, and you should have your process from 1 to 2. And so I don't get a 4 on my homework on that one. And I think it was Nathan maybe that brought that to our attention. I really appreciate it. Okay, anybody else? Any comments or questions?
Yeah, let's see. For negative 10 degrees Celsius, that's a pressure of 201. I was just wondering how that corresponds to our PV diagram.
Well, here, let me put that on there. Thanks for mentioning that. I lost my page already, but I can find it again, I think. Yeah, here we go. At minus 10 degrees, this pressure right here, like, was that Nathan again?
Yeah.
Nathan, this is like you said, it's 201.7 kilopascals right there. That's what Nathan was telling us.
Okay, so we're where we need to be. Okay.
You're okay with that? That was an interesting comment. Anybody else? Anybody else? I don't. Nathan, as long as we're on the subject, we never did put the pressure here at the 50. See that 4064? That's way the heck up here. That 40. 64 kilopascals. This pressure here at 50 is 1318. This is 1318.1 kilopascals. Very good. Proud of you. You guys you're going to do great. Here's your last chance to say anything because I'm hovering over this red button here.
Thanks.
Thank you, guys. We'll see you. What is today? Tuesday. I'll see you Thursday at 11, right? Thursday at 11. It's a deal. Okay. Adios, muchachos.